password crypto problems? No? Yeah. Andreas was a key part of that team that released that white paper. He also traveled a really long way to get here. He's not really taking much time off because he has a vacation next week from Greece. So if he looks jet lagged, it's because he is. And we're really happy you flew out here and took the time to come out and talk to us today. So please welcome him. Thank you.
Thanks for the short introduction. I'm very happy to be here, and welcome to my talk on pen testing iOS apps with a special focus on runtime analysis and manipulation. If you have any questions, I'll be glad to answer them at the end of my presentation. And please forgive me any dropouts. As Jason said, right now it's middle of the night in Germany, so I just flipped.
1 second.
Thank you. Is it better right now? Okay, yeah. I just flipped clocks, and it's a 12-hour time shift, so sorry for any dropouts. Before we start, I have a few words about me on the next slide. I'm currently writing my PhD thesis at the Security Research Group of the University of Erlangen-Nuremberg, and the main focus of my research is based on the security of mobile devices and mobile applications. So for example, we are currently researching new techniques for automated dynamic analysis of iOS apps to conduct empirical studies on the security landscape of mobile apps. And besides my academic work, I'm co-founder of NISO Security Labs, a security research and consulting company based in Germany. We are specialized on software security, doing a lot of penetration testing, code analysis of different kinds of software, from native software to web applications, and a lot of mobile applications in the last years. I'd like to begin this talk with a word on the current state of mobile application security. When it comes to a security assessment of a mobile app, most of the time is spent looking for vulnerabilities in the back-end services. Those of you who have ever conducted a pen test of a mobile app before might agree on that. There are many reasons, just to name a few of them. Most apps are communicating via HTTP to back-end web services, so it's quite easy to adopt all well-known technologies and methodologies from a browser-based world to access the security of a mobile app's back-end component, right? In addition, we have plenty of tools and scanners for revealing vulnerabilities in web applications, and we can just go on using them in order to look for back-end vulnerabilities. Compared to that, there's so far only little information on mobile app assessments, and to make matters worse, we have almost no tools to assist assessments of mobile front ends. So the purpose of this presentation is to enlarge that mobile app slice and to attach more importance on the app itself. And I promise you it's worth it. Within the last years, we're observing a strong increase of client-side security measures inside mobile applications. One popular example is the WhatsApp Messenger, in which I found some serious security vulnerabilities almost 2 years ago. Exploitation of those vulnerabilities allowed you to take over any WhatsApp user account remotely to read messages on their behalf and send messages. And remote means not only in the same wireless broadcast domain, but in the same internet. Yeah? There were serious vulnerabilities in the registration, because the registration of numbers and the number verification actually only took place and happened inside the app. So it's worth to look behind the scenes. To share all the relevant knowledge we gained in pen testing during the last years, I'm going to divide this presentation into 2 parts. At the beginning, I'd like to give you a broad outline on the ObjectiveC runtime. I will show you how running iOS applications can be extended with additional debugging and runtime tracing capabilities, and how this facilitates both dynamic and static analysis of iOS apps. After that introduction, we will focus on different use cases and impacts. So if you are a pen tester, you should be able to explore the attack surface of an iOS app more efficiently. At least I hope so. If you are a developer, you might prefer to avoid client-side logic and security measures in the future. And if you're a decision maker, you should be aware of the emerging risks. Just a few comments on what this talk will not cover. We will not look on vulnerabilities in the underlying iOS operating system, and we won't discuss those basic procedures of app pen tests, as there have been plenty of talks on other conferences before. We are focusing on runtime analysis and runtime manipulation. Let's start with a quick introduction to the Objective-C runtime. Before we have a closer look at the runtime itself, let's talk on Objective-C for a moment. Objective-C was developed in the early 1980s and was the main language used for the next step operating system from which OS X and iOS are derived. And all iOS apps are written in Objective-C. Objective-C provides a set of extensions to the C programming language. These additions are, for example, it's an object-oriented design. We have a strong messaging concept. We'll look at this in a few minutes. A dynamic typing and reflection. You might have heard of reflection in other languages like Java before. Reflection is the ability of a computer program to modify its behavior at runtime. So these concepts make Objective-C quite attractive from a hacking perspective, at least all these runtime functionalities and that reflection abilities. Let's have a look at some sample code. We have a Hello World class which has some memory allocated and is initialized, and afterwards the method sayHello is called just to print out the argument shakaconn. We'll come back to that sample in a second. In the meantime, we'll have a look at the actual runtime. So what makes the Objective-C runtime? During the build process, all apps are linked to the libObjective-C dynamic library. Information on all linked binaries can be extracted from the binary using the object file displaying tool from Apple, and which it will show you that every iOS app is linked to this specific library, this libObjective-C adlib. So this library provides all the runtime functionalities of the Objective-C runtime. And the most important function of that runtime is the function Objective-C message send. So this function serves as a central dispatcher. This function is used to send messages to existing objects. That's the core of that messaging concept. In order to invoke a specific object method, every time a message is sent to that dispatcher, and it routes the messages to the receiving objects. This can be compared to calling a function in C. It's a very fundamental concept. This dispatcher function accepts at least a minimum of 2 parameters. The first parameter is a pointer to an instance of a class whose method we want to call. This is called the receiver or the receiving instance. In our sample, it's an instance of the Hello World class. The second argument to that function is the name of the method that should be invoked. In Objective-C, this is called the selector. In our sample, the sayHello method. In the end, the dispatcher receives a variable list of arguments which is sent to that sayHello method. What's very important, what you should keep in mind is that every method invocation in Objective-C results in one or more messages to that central dispatcher. That's going to be important in a few minutes. Let's talk about how this runtime behavior influences security assessments of iOS applications. As in any kind of software security assessment, 2 different approaches do exist. We have static analysis and dynamic analysis. And while static analysis gives you detailed insights into a mobile app and is of course the preferred way of performing a security assessment, it's not always the most practicable way. Imagine when there's no source code available, or another problem when you have a look at the disassembly of an iOS app, you might notice that the characteristics of Objective-C makes it quite difficult to follow the control flow because of that dynamic messaging concept, which is decided at runtime. In the end, static analysis of iOS apps are quite time-consuming, and we all know that pen testers are always on a tight deadline. So what can we do? The good thing is that the characteristics of the Objective-C runtime enables comprehensive and efficient dynamic analysis. So, for example, we could intercept all those messages to that central dispatcher, and we get a complete clear trace of the internal control flow without having the source code at all. We could also send arbitrary messages to existing objects or rewrite whole implementations of methods, and then we really start to manipulate what's going on inside an app. So we're trying to make use of these techniques. That's it for the short introduction. The important part was that central function of the runtime. Let's move on and have a look at some backgrounds and techniques how to manipulate this runtime. So our starting point, our goal is a black box analysis of an arbitrary iOS app. This could be an enterprise in-house app or an app from the official App Store or a Cydia app. And the typical approach which is chosen for a mobile app security assessment is to examine the app on a jailbroken device. This has many advantages. At first, it removes all limitations imposed by Apple. It provides you root access to the operating system and enables you to install additional analysis software, and it gives you access to the ObjectiveC runtime. So this is the basic procedure. We want to do a black box analysis on a jailbroken testing device. And due to its reflection abilities, the ObjectiveC runtime offers a wide range of opportunities to manipulate existing iOS apps. Before we start to manipulate what happens inside, we need to extend an existing app with additional code. And for this, two different approaches have proven to be extremely practical. We could either inject a complete static library with new functionalities, or we could inject an interpreter for on-the-fly manipulations. Let's have a look on the first one first, to inject a static library. To inject additional code from a debugging library we have developed, we make use of the environment variable insert libraries. This variable advises the dynamic linker, which is a component of the operating system, to load an additional dynamic shared library into the iOS app address space at startup. So this is the first step. Just add additional code, like this. During initialization of that library, the library needs to reroute the program control using runtime patching to make use of our new functionalities. So imagine we have our app, an API method, and our library with providing the additional code. In the case of ObjectiveC, the implementation of that arbitrary method can be replaced. In the case of a C function, we do something like detour runtime patching or pointers whistling and just point that execution over to our replacement. We could call the original API method if we want to, and important is that we could return any value that we want to back to the app. So imagine your app wants to call the unique device ID, we could fake that unique device ID. Or it wants to query your location, we could fake the location. We could manipulate everything which is seen from the app. For this in practice, I'd highly recommend you the usage of mobile substrate. Mobile substrate consists of two parts, a mobile loader and a mobile hooker. The mobile loader will first load itself into the application using that linker technique, and then it looks for all dynamic libraries in a specific folder and DL opens them. The mobile hooker then does the actual hooking. So the function mshook message will replace the implementation of a specific method, and mshook function is the same as mshook message, but for C and C++ functions. If you want to develop those static libraries, I recommend you the use of Theo's development suite to set up your build environment. See the references in the end of this presentation. This is an example of a first tweak. When this library is loaded during initialization, the implementation of the method unique identifier is replaced. This is the method which returns you the unique device ID of your mobile device. And every time that UI device class receives a unique identifier message, it will execute our replaced implementation, which will just return Chaka Khan. So that was the first way of extending existing apps with additional code. Another even more flexible approach is to inject a whole interpreter into an app. And this enables spontaneous, on-the-fly manipulations at runtime. Let's have a look at Script. Script is a programming language designed to blend the barrier between Objective-C and JavaScript. When using Script, a JavaScript interpreter is injected into a running app. Let me show you one example to make it more clear. One of the most powerful features of Script is its ability to attach to an existing process. Not on a debugger level, but on the runtime level. It's more or less a front end to that mobile substrate. And that gives you access to all classes, instance, methods, variables at runtime, and you can invoke arbitrary methods or even replace the implementations within the interpreter. So no need to set up a build environment and compile static libraries, transfer them to your device and so on, just on the fly. So we could attach to an app process, or we could invoke any Objective-C method we want to, like the same as we did before, to retrieve the unique device ID. We could also replace the implementation within Script. It's doing like this. Every time your iDevice receives a message of that type, it will return ShakaCon. And these modifications are specific to the only app in scope we have attached. And when we query the unique device ID again, it will return this static string. This is the app I demonstrate from the App Store, which shows the result of our runtime modifications before and after, just to show you that it works. I'm willing to own that this is not rocket science to just return a faked unique device ID, but it demonstrates the diverse possibilities of iOS runtime injection. During the last years, I had several phone calls of friends of mine in the pentesting community, and they asked me if it's possible just to fake hardware identifiers. In this case, I showed them these techniques, and they were happy. The techniques shown already might be useful in different scenarios. Imagine an app that relies on hardware identifiers for authentication, or a mobile app that uses a binary or a proprietary protocol like Google Protobuf or any binary web service protocol. In the end, you don't have to reverse engineer the protocol. You can just modify some values inside the app. And then you can start the SQL injection attack on the back end just in the app address space. Those manipulations are often very time-saving. Let's look at some more use cases. As we have seen, running apps can be extended with additional debugging and runtime tracing capabilities by using these techniques. This is a great feature to assist security assessments of mobile apps. Runtime manipulation makes it a lot easier for us to discover vulnerabilities and, finally, to prove client-side security measures useless. In the following just one example, more will follow soon. When it comes to evaluate the encryption scheme of an app, a typical question is which app methods are called inside the app after the login button is pressed. So we want to see what happens, although it is a black box assessment. And the idea is to make use of those dynamic analysis features to reconstruct the control flow of an app. To answer that, we want to get a complete trace of all method calls. We could just log all messages to that central dispatcher, right? So let's have a look at the GDB way first. After attaching to a specific app process, we could set a breakpoint at that Objective-C message set function, right, which is here. And every time that breakpoint is reached, we print out the CPU registers R0 and R1. R0 is the first argument to that function, and R1 the second argument, which means R0 holds a pointer to the instance of the class, and R1 contains the name of the method which should be called. So we get always the class and the method, and we get a complete trace of it every time that breakpoint is reached. When we start looking at the output, we recognize very fast that this approach makes an awful lot of noise, because all internal method invocations of the runtime are displayed as well. So it's really unrewarding, and hard to figure out app-specific calls only. We see all the background noise from the runtime as well. A better approach would be to intercept those messages to Objective-C within the runtime. When we hook at the runtime level, we could apply different filters. So using the runtime first, we could extract all available classes and methods from the binary, and afterwards we can focus on app-specific classes and methods only. Not like on a debugger level where everything is printed, but on a runtime level and filtering out all the background noise. The tricky part on this was to handle all parameters and to continue normal execution, because we intercept execution at a very sensitive part at the central dispatcher, and the logging routines itself would modify the CPU registers again. The solution for this is to preserve the current execution state when we pause execution in that dispatcher. For this, we allocate an alternate stack within heap memory. We just back up all the registers and the stack to that alternate stack, and we can do all the logging and filtering and use the CPU as we want to. Afterwards, we restore the registers and continue execution. This was the tricky part, but doing so, no arguments will be lost during logging. We have a stack-safe tracing implementation. And this is the sample output of a password-safe app from the App Store. It shows the trace of app methods after a user has entered his passcode. And what we can see very quickly is that only a constant string is used for decryption and not the user passcode. This is bad crypto implementation. I also call your attention to that key derivation function. At least the developers try to derive a strong cryptographic key out of a constant string. Questionable, but however, so hopefully that constant string was guaranteed to be random and nothing could go wrong. So within seconds, we have evaluated the encryption scheme of that app without the need for doing any static analysis, right? Runtime analysis can be very time-saving during a penetration test. That was just one example on how runtime manipulation assists security assessments. Let's look at some more. So we had that discover weak missing encryption. We could bypass any client-side restrictions. We could execute hidden functionalities which was not supposed to be accessible at all. Or we could unlock additional features and premium content. Imagine apps where there's a light version and a pro one. Often the light version contains the same code, but the pro features are simply not accessible within the user interface. Now you know how to upgrade your light version. Or imagine an app, imagine all these in-app purchases. Most of them are broken by design. So they're just waiting to be enabled for free by executing the specific method, which is called from a callback from the iTunes store. More than 80% of the in-app purchases can be retrieved for free. It's also very interesting when apps deal with copyright protected content like pay TV providers, newspapers, and also on. All those data, like movies, are accessible at runtime when you can watch them, and you can simply dump them and copy them using all those techniques. So to sum up, runtime manipulation increases the attack surface of mobile apps. It assists security assessments, and even new attack vectors might arise. The only problem is that there are almost no tools available for those dynamic analysis. Although you know the techniques and you could compile a static library and so on, it would be quite time-consuming, and you wouldn't do that on your daily pen testing basis. And as Josh Wright said, and I like that, security will not get better until tools for practical exploration of the attack surface are made available. In the following, we will close that gap of missing tools. So during the last years, we have developed several little libraries and penetration tests. We call those debugging and runtime tracing. However, it was quite time-consuming to maintain all those little tweaks and to keep an overview. This is why we decided to consolidate all these little helpers into a comprehensive debugging library. So what you need to do is catch your testing device, install an app, and get our library on it, with all the debugging and runtime tracing functionalities. To make all these functions in that library accessible and very easy to use, we extended it with an XML RPC web service endpoint, which is started inside the app. And we also start a web server in it, and this web server provides you with an HTML JavaScript front end based on Google Web Toolkit, and this front end communicates with the web service to remotely control and manipulate any arbitrary iOS app. That idea was the birth of Snoopit, a tool to assist security assessments and dynamic analysis of iOS apps. Let's have a look at some features. We could monitor all file system accesses as we're hooking all open system calls to the kernel. And using these features would be very easy for you to spot configuration files that store sensitive data in clear, because you see every access to the file system. You could apply different filters on it. You could even see if Apple's data protection mechanisms are used or not. We see all accesses to the keychain, access to sensitive API, like when an app accesses your address book or your location, your photos, and even when an app tries to access your microphone. Did you know that it's only a few lines of code to switch on your microphone and to send that recording to a backend web server? And you have no way to restrict that on your iOS device. This is going to be changed in iOS 7, and user consent is required to access the microphone, but at the moment it's completely missing. We could fake hardware identifiers, fake location, GPS data. A short story on that. I had to assess an iOS app which was supposed to only work on the company grounds of that company. So a typical client-side security measure. So I had two choices. Either I could travel abroad, or I could find a way to fake GPS data to this app and sleep at home. You might guess which option I had chosen, and the result is also integrated in Snoopit. You could fake any specific location. It's also a good feature to make fun of friends. You could explore all view controllers, list all available classes, invoke methods at runtime. Just a few other features. We pay a lot of attention to make it very easy to use. So after installing that package, you will get a configuration app. I'll show you that in a minute. Then you could use that web interface with different filters. We also provide you with an XML RPC web service interface and a detailed description of it. So you don't have to use our web interface. You could just use your Python or Ruby script or whatever to automate your own analysis. And it will be freely available soon. If you're interested in a beta, just send me a mail, I think within the next few weeks. To get started, you just have to open the Snoopit configuration app, select the apps you want to analyze. Could be from system apps from Apple or App Store apps. Adjust some settings, like the web server listener port, and just run the app you want to analyze and point your browser to the Snoopit web interface. Let's do a demo on it. All right. What you see here in the lower left is that Snoopit configuration app. Just have to open it, and then you can select the apps you want to analyze. Let's do a quick assessment of that flashlight app. In the settings, you can set the web server listening port, some authentication, and the tracing. We'll come on that later. And after that, you just have to switch on and open that app. During startup, using that library injection, our debugging library is injected inside this flashlight app, and the web server is already running. So I can just now connect to it. And this is the web interface. Now it connects to the web service interface. We can see some memory protection which is used inside. We can see all the NSLog debugging outputs which developers might have forgotten to remove. And let's look at these file system access. We see every access to the file system, and we restrict it in this view just to the application sandbox. Using this filter, you can also see all the background file system access of the iOS operating system. And you see every file which is loaded, and we also print out the Apple file protection classes to spot files which are not using Apple mechanisms, also indicated by a red dot here. Access to the keychain, access to network, and just want to remind you, this is a flashlight app, just to switch on light and switch it off. And it does a lot of network communication. It has at least 4 different tracking services libraries integrated. Those tracking services are a really bad thing. More than 2/3 of all apps are using those statistic and tracking services, and they keep track of every action you take. So when you start an app, they send a request. When you tap a specific button, they send a request to the backend. So very transparent when using any mobile app. So let's see here one of these requests from the tab Choi Ad Network. It transfers my country code, my iOS version, and let's go further to the end where it says my provider, the German Telecom, tracking enabled, my advertising ID, platform is iOS, my device's MAC address, my device name, and it would transfer also the location if I would have allowed the app to access the location. But then all tracking services can access your location as well. Keep that in mind. So just a privacy issue in that flashlight app. We see all access to sensitive API, a lot of access to that Wi-Fi MAC address. You know why, because of these plenty of services. This will stop in iOS 7. In iOS 7, Apple will return a static value when an app tries to access the MAC address. Always return 0000. So I'm quite curious what the tracking services will move on next. We see some access to the camera. We can fake hardware identifiers very easily. We could also pretend to be an iPad or an iPod. We have here that fake location. You just set a pin, and afterwards the app would think you are at this location. This is a feature where we extract all available class and method information out of the binary. And these are all the classes and methods which are implemented in that flashlight app. During initialization of each class, we keep track of that just to invoke methods of instances, which means a green dot indicates that this is a concrete instance we catched and we know the location in memory, and red means it's just a class. We could just click on this instance. These are all the methods which are provided. Could open the function, could invoke the function open camera LED. Just need to select an instance which we catched, and then we could invoke that method. And this is the only way I really can prove that it works to remotely control that App Store app. Otherwise, everything could have been fake, what I've shown you. But it really works. Without the need for any shell, very easy to use. Let's do another example. Gonna switch back. Is any one of you using this iPin Lite or iPin password safe? No one dares? So you have nothing to fear. This app, I just want to give you some of these description. It says, with an innovative sensor keyboard, you'll have quick access to all your pins without any annoying and time-killing passwords. Sounds great. Sounds like a perfect example of usability meets security, right? On security, it says, safety is of greatest importance. All data is encrypted using AES, and they apply the KISS principle, keep it simple and secure. So let's look behind the scenes, and let's analyze this application from the App Store. For this, we just enable it, and I want to use that tracing feature now, just to look behind the scenes, what's happened inside the app. Now we can start it up. It loads. Now our library is injected, the web server is started, and this is what it looks like. The question is, where are all these secret data stored now? On the first spot, we would go to the file system and look for any suspicious file system activity. What we see is there are many of view controllers access, some localizable strings, the sensor keyboard view controller, which presents you that sensor view, and a file which is called iPin security model. That sounds very interesting. Using Snoopit, you could just download that file by a double click, so no need to secure copy that file, and you open it. But the best thing would have been if it's here in clear, but unfortunately it's encoded or at least encrypted or anything. So, but the good thing is we have that method tracing feature, and we can now look at the methods which are processing this file. So let's look at that method tracing. We can see what happens after we have started the app. Just increase size, and now let's look for the security model, which was the name of that file. What we see is that this file is really accessed, and the problem with it is that this file is some kind of packed, and the archive is protected with a key, and the key to unpack that file is IPIN model. So this is the first problem. It's a static password used for unpacking or decrypting this file. What comes out of this file is, in this file is stored a sensor hash. Okay, what is this hash used for? Obviously for authentication purposes, just to verify if the entered sensor code is correct or not. Might be just an assumption. I copy that, so we'll use it soon. Now let's go to the end and have a look what happens after we press a single button. The upper left one, reload, and see all the method invocations. There are plenty of invocations, although we do a lot of filtering to get out all the background noise. Just looking for it. There must be a touched event. Yeah, here it says set touched. Number of touches 1, this method is called. What we see here, that sensor keyboard view controller returns a value of 10. Here it is again, it's given over to the login view controller, and afterwards an MD5 hash is calculated of that value of 10. And afterwards it is compared to the sensor hash, which was derived from that file, protected with that constant string. So what happens is every time you tap a single sensor viewer, it is joined to a password, and the MD5 hash is calculated and compared to that one. But on these 9 different fields, the number of combinations is quite limited, right? So I wrote a small Python script just to brute force all possible combinations from 10, 10, 10, 10, 10 to 90, 90, 90, 90. And I will give it that sensor hash, which we have derived from that file. And it only took you a few milliseconds to derive the sensor code, which was in that case 10, 20, 30, 60, 90. So within seconds, we have analyzed that password safe app without the need for doing any static analysis, just by looking at the trace and by invoking methods at runtime. This is very time-saving. So I hope you enjoyed that demo, and during the last weeks, we got a lot of positive feedback from our beta testers. Snoopit is used by pen testers all around the world now. I put it one feedback on this slide. And even several companies in Germany are using Snoopit to review App Store apps for privacy violations before whitelisting apps and allowing them for internal use, just to get sure that no contacts are accessed and not the microphone and all that stuff. Another use case. Last week we published a study on the security of mobile hotspots. Using these dynamic analysis techniques, we analyzed the official preferences app from the iOS, and we found out that iOS generates weak default passwords when an iPhone is used as a mobile hotspot. On a first spot, default passwords consist of only 4 to 6 characters, followed by a 4-digit number. And this enables brute force attacks on the VPA handshake. In more detail, we observed that the iOS spell checking framework is used to suggest a default password. This is why default passwords are derived from an English language dictionary. But Apple did 2 more mistakes. We found out that only 1,800 entries of that dictionary are taken in consideration when choosing a default password. Compared to the number of sold iOS devices, 1,800 different passwords is quite limited, right? And in addition, the process of selecting words from that dictionary is not random at all. This results in a possibility to compromise a hotspot connection in less than 50 seconds. This shows the frequency distribution. It shows very clear that words from the top 10 are 10 times more likely to be selected from that limited word list at all to be used as a default password. And this is the top 10 of default passwords of iOS Hotspot. So if you didn't change your password by now, just have a look. If your password is one of these, I highly recommend you to change your hotspot passwords. For more information, please refer to our chair's website. I think this serves as a perfect example why it's always a good advice to replace initial default passwords by user-defined strong and secure passwords. By the way, we have notified Apple long time ago, and this is going to be fixed in iOS 7. And it looks quite random. We hadn't a look on this yet. One more thing, the last thing. More and more apps perform some kind of jailbreak detection to verify the platform integrity. Mainly banking apps or movie apps or apps of mobile device management solutions try to detect if they were executed on a jailbroken device. For that, they perform common checks like looking for suspicious files and directories like application Cydia app, look for file system permissions, mount options, just for traces of public jailbreaks. The problem with these checks is that all of them rely on information provided by an untrustworthy runtime to determine its integrity. That will never work. It's the same as you were trying to detect a rootkit on a host operating system from within a virtual machine. Yeah. This is what a jailbreak check looks like in static analysis. Oh, it's hard to read. So what we see here is a else-stat system call on the applications folder, and it tries to detect if all applications lie in the applications folder or if the applications folder is a symlink to the user partition, because this happens at a jailbreak. All the applications are moved to the user partition. And afterwards, the file etcfstab is accessed and is searched for if it's readable or read-write access on the root partition. It's also a trace of a jailbreak. So this is what these checks usually look like. Since we are testing apps on a jailbroken device, we need to bypass all those checks in order to assess them. So we could either patch an app binary offline and patch that jailbreak detection out, or more easily at runtime to remove their checks. So if you have a very easy check, you could just do like this in script. Every time your delegate receives a message, is jailbroken, just return no. So in many cases, it's as easy as this way. A more generic way would be to intercept all system calls to the kernel and to simulate an unmodified execution environment. This would be a generic approach, and this is what we do in Snoopit. To hide Snoopit from its surrounding and to bypass most of the common jailbreak detection mechanisms available, we hook all major system calls and pretend an unmodified execution environment. And to activate that bypass, you just have to switch it on inside the Snoopit configuration app. I will show you that. We have here an app which is called 3D Central. I have no clue what this app is for, but it performs a jailbreak detection, so good for demonstration purposes. And it says jailbroken devices are not supported and I can't use that app any longer. And that disassembly you have seen is just a disassembly of this application. Now I will open Snoopit, and going down we can switch on the bypass jailbreak detection mechanism. And then I'm going to restart that app, and it will just boot. So it makes all these checks, but we fake all the values that are returned to that app. So this is quite a useful feature to not wasting too much time during a penetration test on disabling the jailbreak checks. Last week we examined the jailbreak detection mechanism of mobile RN and Good for Enterprise, and we broke them within a single day. So I recommend you to not rely too much on those jailbreak detection mechanisms, especially in bring your own device scenarios. How could one do it better? We researched some techniques for advanced jailbreak detection and developed AppMinder. AppMinder is a jailbreak detection which is written in pure assembly code. We only used ARM assembly to implement it just to avoid getting hooked these easy techniques using mobile substrate and so on. So we put a lot of effort in various code obfuscation techniques, so that makes it hard to spot that jailbreak detection at all. Even IDA crashes a lot of times when that jailbreak detection is integrated. A lot of self-integrity checks, anti-debugging measures, and it's provided as a web service at AppMinder and Nisolabs. There you can just have a look on it. It will give you a small interface. You could click on generate and you get your own jailbreak detection code. The code is polymorphic, which means that every time you click generate, you will get your own code. So even we can't bypass it. Of course, all those AppMinder checks can be bypassed as well if you do something like kernel hooking, or if you would just invest a lot of time to spot it and to bypass it. So this is why we raised the bar for this very high. I don't want to bypass these checks. So this is what it looks like. You have different levels of obfuscation and self-integrity and so on. Just use it. If you have any questions on AppMinder, send me an email. To conclude, I'd like to discuss some countermeasures for securing the runtime. The first commandment, of course, is keep only a minimum of data and logic on the client side. So at least no client-side security mechanisms. Those can be easily bypassed our tools. If you develop some apps, make preferred use of C, at least for security critical implements. ObjectiveC can be hooked very easily. C can be hooked not as easily as ObjectiveC. And you can use something like inline functions, and more obfuscation is possible within ObjectiveC. And do some kind of advanced jailbreak detection and runtime integrity checks. At least try to. It's worth a shot, and you always should raise the bar as high as possible. Well, what I want you to take home is that runtime analysis and manipulation facilitates both dynamic and static analysis of iOS applications. Just remember these examples where we've analyzed an arbitrary App Store password-safe app within seconds. The attack surface of iOS apps can be explored more efficiently using these techniques, and even with our new tool Snoopit, which will be provided soon. So for your future iOS app assessments, this means when in doubt, snoop it out. Thank you very much. Are there any questions or comments on it? All right, I'm around until this afternoon, so just come to me and let's have some mobile app security discussions. Thank you.
Thank you, Andreas. Another round of applause for him. That was pretty awesome.
Thank you. All right.